All video cameras have a limited temporal resolution. When objects move too quickly, they cannot be resolved. In this video, we show a technique for resolving high-speed periodic motions using consumer-grade video cameras. Our system records linear combinations of radiance values by opening and closing the shutter during exposure. It can be implemented directly using the commercially available point-gray Dragonfly 2 camera. Even finer temporal resolution for the coated strobing shutter can be achieved using a DisplayTech ferroelectric shutter. For example, here is a tool in a mill rotating at 3,000 rotations per minute. On the left is a video taken using a normal 10 Hz video camera. The image is completely blurred as the tool makes 5 revolutions during each frame's exposure. Using our method, we can reconstruct the high-speed video, as shown on the right. The reconstructed video has a temporal resolution of 1 frame per millisecond, 100 times faster than the normal video. According to the Nyquist sampling theorem, in order to faithfully reproduce a band-limited signal, the sampling rate must be twice the maximum frequency. Generally, this requires expensive high-speed cameras. In this paper, we look at the class of periodic signals and show how to go beyond the Nyquist limit while reconstructing such signals. It can be shown that if a periodic signal has a fundamental frequency of f sub p, then its Fourier representation contains energy only in the frequencies that are integer multiples of f sub p. This means that all periodic signals are sparse in the Fourier domain. We later will show how to exploit this sparsity in our reconstruction algorithm. When a fast-moving periodic signal is measured by a normal camera, the signal is integrated throughout the frame duration, resulting in blurred videos and unrecognizable motion. Expensive high-speed cameras are capable of capturing the signal, however, their high bandwidth is mostly wasted, as can be seen in this Fourier domain illustration. Another successful technique for capturing and displaying high-speed periodic signals is stroboscopy. In stroboscopy, a strobe light flickers at a frequency very close to that of the signal. This aliases the signal to a lower frequency that can be more easily captured or displayed. However, this technique requires prior knowledge of the signal frequency and is light inefficient. In our approach, we measure linear combinations of the periodic signal by coding the exposure during each frame of a normal video camera recording. This allows us to take advantage of the sparsity of the signal in the Fourier domain during the reconstruction phase. In particular, we extend algorithms developed in the field of compressive sensing in order to reconstruct the sparse Fourier coefficients from the measured linear combinations. For further details, please refer to our paper. In order to validate our algorithm, we examined the animation of a fractal called Julia. On the left is the original, full-resolution animation where each frame is of 1 millisecond duration. On the right is a video synthesized to demonstrate what would be obtained by a 10 frame per second video camera. Next, we simulated capturing the animation with a 10 frame per second coated strobing camera, as shown in the lower left. In the lower right is the reconstructed animation obtained by our algorithm, which, as you can see, is visually identical to the original animation. Notice that in this simulation, we were able to obtain 1 millisecond time resolution from a 100 millisecond sampling in the capture process for an upsampling rate of 100. Since high-speed sensing is always light-limited, we also performed statistical analysis regarding the robustness of our algorithm to sensor noise. As you can see, even with significant amounts of noise, the reconstruction is reasonably robust. As can be seen in this figure, using our approach can improve the time resolution of periodic signals by upsampling factors on the order of 100s without significant degradation in reconstruction quality. In this example, the toothbrush oscillates at a fundamental frequency around 62 Hz. The coded strobing frame rate is captured at 20 frames per second for a 50 millisecond frame duration. We were able to recover 1 millisecond resolution for an upsampling factor of 50. It is worth noting that the circular part of the brush does not rotate completely, but instead swivels back and forth. These are the reconstructions obtained from our 9 frame per second coated strobing camera when the mill tool was operating at 3,000, 4,500, 6,000, and 12,000 rotations per minute. Notice that since the limit of the temporal resolution of the capturing point-gray camera is 1 millisecond, the 12,000 rotation per minute tool looks blurred even in our reconstruction. In conclusion, we have shown a new method for capturing high-speed videos of periodic signals using low frame rate cameras and coded strobing exposures.